we'd like to thank our sponsors. And what M-OSRP is about, the research purpose is to identify and address pressing seismic challenges, prioritize challenges. And why are there challenges? There are challenges because all methods, without exception, make assumptions. When those assumptions are satisfied, the methods are effective, and when they're not satisfied, those methods have problems, and they can fail. And that can contribute to dry hole drilling or suboptimal development drilling. So what are the types of assumptions? There's assumptions about the type of data that is required for an algorithm to be effective. Then we have enough compute power to make the algorithm relevant. There is a reasonable turnaround time. And then there's a third type of assumption, which is the assumptions within the algorithm itself. What is the algorithm assuming is satisfied? Prerequisites, subsurface information, interpretive information. It's not that you can't blame on acquisition or inadequate compute power. So there's two ways we see to address a challenge. If you have an assumption that's having a problem, you can remove the assumption violation by satisfying it. If a depth image needs a velocity model, and one way, if you're having problems with providing the adequate velocity, then find a way to improve finding it. That's one way. Another way is to avoid the assumption violation by developing a method that doesn't have that assumption. We generally recommend to people, young people in particular, to do the first if you can. Or if people believe that something is needed to achieve a certain seismic goal, then they will, it's easier to get support for research that tries to improve that assumed requirement rather than to try to explain that it's possible it's not needed at all. That's a tougher thing to try to convince people of. They have a big investment personally, technically, in being expert and trying to find that requirement. And it's a more difficult road. So you, only when under duress should you go the second route. And we see at times the need for that. And we have at times assumed that second attitude. But in general, we don't take whatever an algorithm requires and assume that we can figure out a way to avoid what it requires. There are certain requirements that we look to improve the satisfaction of the requirement. And there are other requirements that we look for a new algorithm that doesn't make that assumption. And so, basically, if you had to say the one assumption that is consistent within M-OSRP, is one very important exception that you'll hear about, in particular tomorrow, is that we are looking for methods that do not require subsurface information. So if it's for a prerequisite like deghosting or wavelet estimation, separating the reference wave from the reflection data, then if the method requires those steps, in those cases we look to satisfy that requirement. But the method of satisfying the requirement does not assume you know anything about the Earth. So when we satisfy a requirement, or we look to avoid a requirement, we have the same attitude that no subsurface information should be required. So the reason is that increasingly the ability to provide detailed subsurface information has become a growing challenge in the history of multiple removal. If you look at the early history of stacking and FK filters and radon and high-resolution radon, at every step in that evolution, there was an increase in the need for subsurface information, details, and the evolution of migration from post-stack to pre-stack time to pre-stack depth to migration aversion to RTM. At every step in more capable imaging, you had a commensurate and associated greater demand for subsurface information. And as industry explores in more complicated, difficult, challenging environments, offshore, onshore, more frequently that ability to provide subsurface information is not attainable. The big change in seismic processing in terms of multiples was the shift suddenly to a set of methods that did not require subsurface information. That was a major shift and change from an evolution which at every step required more and more, suddenly not at all. And so we'll examine some of that evolution in terms of what it has been able to achieve, and more importantly, what it has not been able to achieve. We need to have a frank discussion about what the open issues are, issues that some of which we don't know how to solve. And so we expect a maturity that's associated with the frankness that will tell you that here's a problem we don't know how to solve, and but we're going to. Rather than saying, you know, every single problem that is there is the problem that we are working on and know how to solve. That is not the case, not here. And in fact, it isn't the case anywhere in seismic. It's whether you're told that that's the case or not. It's the only difference. Okay? So there's a danger in what I just said. There's a danger for us. Because sometimes people will hear, this is what they can't do, go back and report. This is what they can't do. That's the summary. That's we'll live with that possibility. Okay, so we're looking for a consistent and aligned linked set of processing steps. And every step in the processing chain should be consistent, and every step in the chain should be cognizant of future steps and work to support them, align with them. So this is a cartoon of marine events and the steps that data, is this a pointer? Imagine this is marine data that's just been acquired. And then what happens is in this seismic processing chain, a set of separations of events into different catalogs of types of events. This receiver in the ocean receives seismic data. And then the first step is separate the events that have bounced off the free surface right to your receiver and straight to your receiver. This we call a reference wave. Some people would call that the direct wave. This wave has not experienced the Earth, and so we separate it. It has information that we use, we separate and utilize. And then there's all the data that has reflected from the Earth. The step after this separation between reference wave and reflection data, or what we call scattered wave, is we separate all reflection data into data that has ghosts and data that is not ghost. A ghost means an event that started its history moving up from the source to the free surface and down, or moving down from the free surface when it's recorded, or both. So these events are separated, ghost events are separated from non-ghost events. Non-ghost events start their history moving down from the source, and when they're recorded, are moving up at the receiver. So this separation occurs using Green's theorem. Every dot here that's green means Green's theorem can achieve it. Every dot with the yellow means the inverse scattering series can achieve it. Whether it's green or yellow, the achievement here is without subsurface information, with one exception, this one. We'll get to that in a minute. So after you have removed ghosts and the reference wave, first you remove this, then you deghost the reflection data. Then you take the deghosted primaries, free-surface multiples, and internal multiples, and separate out free-surface multiples from primaries and internal multiples. And then one step again, primaries separated from internal multiples. Then primaries used to find a depth image without a velocity model. And to do direct AVO, again, without a velocity model, Q compensation without Q. Here is the exception to this overall rule. We wandered into this topic by accident in terms of looking at Green's theorem expressions for wave field separation and wave field prediction, and realized that there was no wave equation migration, RTM, no theory that predicted what a source and a receiver experiment would do at depth, and then make them coincident at time equals 0 in a medium where the waves are moving down and up. All the RTM methods are asymptotic in the sense of Theorem. So we'll discuss that. Since there's such a wide use of RTM in the industry today, we felt it was reasonable to report that news and explain exactly what we meant by that. RTM uses the wave equation. How can it uses the wave equation in bringing the data down and bringing the source field forward? How can it not be a wave equation migration? The reason is the imaging condition that's used puts it into Kirchhoff land. Does not produce a source and receiver. The current methods for RTM do not produce a source and receiver experiment and then time equals 0. Why is that important? Because nothing compares to a source and receiver experiment predicted above a reflector to get amplitude information. Nothing. So if it isn't that, you're getting something that you'll see examples. You cannot do amplitude analysis. You can, but there's no physical basis for it. And you'll see the consequences by example tomorrow. Okay? So that's the only deviation from this rest of this chart, which moves without subsurface information. So since there's a big part of this chart that involves Green's theorem, what the plan of the meeting is as follows. I'm going to give a tutorial on Green's theorem, just to give you some sense of how that works, how these kind of wave separation methods work from Green's theorem, a hint at the wave prediction methods. More detail will be given tomorrow as a introduction to wave equation migration RTM in terms of what Green's theorem says about how to predict a wave in a medium where the wave is moving in two directions. But today the emphasis is going to be for those preprocessing steps, wave separation methods. How does Green's theorem arrange that? Why is it important? So after there's some kind of tutorial on that, then we'll give again a brief tutorial on the inverse scattering series, and including where are we today with multiples, and where aren't we, and where do we need to be, what's our plan to get there. And once we have that communicated, then will go through the agenda, showing you where different parts of the strategy to deal with the current lack of capability in multiples is being addressed within the group. And then we'll move to ISS. That's going to be a big part of the meeting, because multiples have moved back to center stage for M-OSRP. When I arrived at U of H in 2000, 2001, I was sick of multiples, sick of chasing them. Okay, we've done that all. I wanted to do something. So we did the multiple business because sponsors wanted code. They said, you might be sick of it, but we're not sick of it. Just deliver code. And that will pay the rent while you do whatever you're interested in. Okay? So what has happened, though, is we're very happy that methods developed from M-OSRP are considered top capability today. I will give evidence for internal multiple in particular. But we recognize that what we have delivered, which is the best available today in the industry, is inadequate, fundamentally inadequate when you have multiples on land and many times in the marine setting where you have proximal and interfering events. And there is no capability today, starting with M-OSRP, that can effectively address it. That's just the fact. You go look in the Middle East, every primary seems to have a multiple on it. And it's not just there. You have many times in the offshore with interfering events. The methods today that are available from here, which we feel on top of the line. Why do they stand alone? Because they do not depend on subsurface information, no interpreter intervention. The internal multiple is an attenuator. The internal multiple code that you'll see is an attenuator. Attenuator means it reduces the amplitude of the internal multiple, but not eliminate. So what happens in the real world is after that is carried on, to deal with the fact that it is first not an eliminator, in principle not an eliminator, to deal with the fact that often the prerequisites, the wavelet and deghosting and all the other, are not fully supplied. And in addition, there's real world, always real world issues that are outside your physics. Water top is not a free surface, it's not flat, the cable has feathering, it's finite sampling, limited aperture. Everything that your theory didn't anticipate, you need some dial to deal with. And they throw that all into the adaptive subtraction step, energy minimization, adaptive subtraction. That idea, Eric Couture and Booth pioneered it. Howard Bavalio Zia advanced it beyond that global search method. And it works well if you're multiple and other events are not near each other. You have an actual multiple, you have the prediction, you adjust this in amplitude and time to subtract. The idea being, if you have multiple in a region, and then the multiple is not there, you have less energy when the multiple is not there than when the multiple is there. So you look for some way to reduce the energy in a time interval. And that is a often very useful idea, except when events are near each other. When events are near each other, proximal, if they're proximal, it's too blunt an instrument. If they're interfering, you'll see an example of a completely destructive interfering primary multiple. It's invisible. You can't see anything. When the primary comes up, your energy has gone up, not down. Because they annihilated each other. There was nothing there. And after the multiple removal, the energy went up, not down. So the whole criteria of that energy will be minimized, reduced. Is great when you have separated events. It is not a solution when you have proximal interfering events, and there are many times when that's the case. we have a strategy here for addressing that problem. And a major part of the meeting here will be showing you pieces of that strategy, the progress we've made towards each of those pieces to address that specific issue. Is that clear? In other words, okay. So, what I'm going to do, I think, is I'll give you the tutorial on Green's theorem, mainly for wave separation methods. Some of those early steps up there. Then we'll take a coffee break, or whatever break, and then we'll go into the ISS. Where does that promise come from? There's one set of equations that says every processing objective that you can imagine is achievable directly and without subsurface information. And so that's, where is that? Where is, all we're doing is mining it, saying where are certain different tasks within that big promise, extract them and use them. Okay, so let me start. Are there any questions before we start with comments? So this is a tutorial on Green's theorem, for all those green dots of wave separation methods. So these are on the right, the wave separation is, as we said, reference wave separating from reflection data, predicting the source signature radiation pattern, in other words, the nature of the experiment, and source and receiver deghosting. All of these are forms of wave field separation methods that we use Green's theorem to realize. For wave field prediction, as I mentioned, we'll have more to say about that tomorrow. For wave field prediction, Green's theorem for wave field prediction says if you want to predict a wave inside the volume, you need to know the medium above that point that you want to predict. The medium, not the velocity, the medium, everything about that medium. Velocity, density, absorption, everything. Okay? That's what Green's theorem says. And if predicting the receiver at depth is one step towards wave equation migration, predict the receiver, predict the source, make them coincident at time equals 0, then Green's theorem says the migration needs subsurface information. We respect Green's theorem, but it's a theory. It's a theorem. In Morse and Feshbach, chapter 7, it's written like a chart, like it came from Mount Sinai. It doesn't say Green's theorem says it. It says this is what you need, period. Okay? And then when you look for why you need it, you see it's those consequences that derive from Green's theorem. The point is, it's a method. Methods have assumptions. The inverse scattering series is another method. It says you don't need that information. It's a very different kind of thinking and a very different kind of use of data, and it's not magic, and it's understandable, and there'll be another theory someday, hopefully soon, that will supersede the inverse scattering series. It's the nature of things. So methods have assumptions. It doesn't mean that those assumptions will be required by any method. Everybody understands? And Green's theorem is correct, and the inverse scattering series is correct. They're different, and they use data very differently. And they use different aspects of the data in achieving their goals. One with subsurface information, and one without. Okay, so we're going to illustrate this Green's theorem business in terms of an acoustic equation. Green's theorem and these consequences is not an acoustic method. We're just using this. You can write this for elastic, for electromagnetic, for any differential equation where you have terms on the right-hand side that you can consider sources. So, but we'll illustrate it with this equation. Equation 1 represents an acoustic wave of pressure P source located at RS, and RS, field point R, single frequency, omega, a wavelet, assume A of omega, this is source signature, and we assume it's localized at some point, the source with some time function. And it's heterogeneous, it has a variable velocity. The first step to go through this is we're going to take this velocity configuration and we're going to reconfigure it in this form where C0 is a reference velocity chosen here to be constant and need not be, and this parameter alpha, which is then in some form of perturbation. In other words, where alpha is 0, C of the actual velocity is the reference velocity, and when they're not equal, alpha is not equal. So alpha carries the difference between actual velocity at a point and the reference velocity. And K is just omega, is temporal frequency over the reference velocity. So after you make that substitution of describing the velocity in terms of reference and this perturbation alpha, after you put this form in here, take this part and put it on the right-hand side. Put the alpha part on the right-hand side. You get this form. Then we're going to treat this right-hand side as sources. In other words, as if this was some kind of differential equation and these were driving terms. So the picture here is you have a reference medium, C0, and these guys here are sort of dropped on the reference medium and are the source of either the wave itself or the source of the wave that gives the difference between the reference wave and the actual wave. So this right-hand term we're going to call rho, a general source, rho. And then this equation is written as this homogeneous operator with rho here, where rho gives you everything that you need to add on to a homogeneous world to make the real world. Meaning you have to add on to the homogeneous world the air guns and the fact that the real world is not C0. That's in rho. Now it's useful, it turns out, in these descriptions to write an equation like this, except where you make rho be some idealized local source. That entity is called the Green's function. And this looks just like the P equation, except instead of rho, you have this localized source at one point. Then the idea here is we're going to construct descriptions of the actual field P in terms of this idealized Green's function impulse response to an impulsive source at one point. And to express P in terms of G0 turns out to be useful. So the first thing is, if you can write a combination of G0s in terms of the weights, rho, in equation 4, and you get this equation. This equation, if G0 is picked to be causal, meaning just exploding, the source goes off and a wave emits from a causal Green's function. In other words, this equation has an infinite number of solutions. One among them, this is an inhomogeneous differential equation. And it has an infinite number of solutions. Among the infinite number of solutions, one of them is causal. That, if you put that in this expression, and you take this weight, which is the source in the P equation, you get P. How do you know? If you put del squared plus k squared on the both sides, del squared plus k squared acting on G0 will give you delta. And since this integrates over the whole space, you're going to get del squared plus k squared P is rho. And in addition, that just tells you that this gives you a solution. In addition, if these are the causal solutions, this is not just a solution to the P equation, it's the causal solution, meaning it's a superposition of weighted causal solutions at different points offline. So this is the argument here comes from linearity and superposition. And if you're interested in the physical solution here, this must be expressed in terms of physical solutions, meaning causal solutions to this equation. So that's one relationship, a very important relationship. It says, if you want to know that the medium here, in other words, a wave field depends on the medium. We decided to describe the world in terms of a reference medium and sources. This comes from the reference medium, and here's the sources. The reference plus sources gives you the world. P, the actual wave anywhere, if you give me the sources everywhere, this will give you the field everywhere. That's the idea. There's another form. This owes its this mean second identity. It comes from a totally different thinking due to Isaac Newton and Leibniz, and it's very different, very profound, with much mystery. It comes from fundamental theorem of the integral calculus. And then you get, grows up to become the divergence theorem. And there are different, this is for an integral of the divergence. Every point inside a volume is replaceable by something else on the boundary. An integral over an integral, replaceable by something else, the antiderivative of this. That is just this. So this activity came from Isaac Newton and Leibniz, roughly at the same time. Has nothing to do with linearity or superposition. It's a math statement, but an amazing statement. So we can apply, this comes from the divergence theorem by just taking P, A there equals P grad G0 minus G0 grad P, and you find this. So this form is for P and G0 under very general conditions. At this point, nothing about what they mean to us has ended. To make them mean what we mean by P and G0, you substitute for del squared G0 and del squared P their differential equations on the previous page, and what you end up with is an expression for when R is in the volume, you get a P for R in the volume is a volume integral over the sources in the volume plus a surface integral. This is only valid, this is only an expression for the field in the volume, for the wave field for a point R in the volume. What's the volume? What you have decided to integrate in the some volume, any volume, and this is the closed surface that encloses it. If you take the right-hand side and evaluate it for a point outside the volume, the sum of these two is 0, not the field. Discontinuous. So this is just a simple realization of that former equation. This is a tremendously, this is an amazing equation. It forms the basis of all the wave separation methods, all the wave prediction methods. So it's a lot to say. One of the mysteries, amazing, even no matter how many times I've done examples, is the following. as long as you have a surface integral here, that's not zero. As long as you have a surface integral that's not zero, then you can pick any G0 that satisfies that differential equation, del squared plus k squared G0 is delta. Any one of an infinite set of solutions. Pick any one you want. Causal, anti-causal, causal plus anti-causal over 2. Nothing to do with causal and anti-causal. Any solution, and this will be the physical solution for the wave field in the medium. That's mind-boggling. Okay? It's essential for migration theory to understand for how Green's theorem speaks to, for example, slope migration and how one-way waves, in other words, and then how Green's theorem gives you wave equation migration RTM. So why is that true? To give you a hint is when you say that what is this P in grad P dot n? Those are values of the field on the surface. If they are actual, it nails it. That's why I say, if this is here, okay? If this is not there, in other words, if for some reason you just have an expression on the volume, as you did for the whole space, then you must have causal superposition. If you don't, this becomes a boundary value problem, where you made a unique solution by boundary measurements, okay? By measurements, okay? This is assuming that P is found in the volume by integrating over the sources in the volume and some surface integral here, where the surface integral has values of the actual wave field and its normal derivative. Those last words are what make it not care what G0 you choose. Okay? That is far from obvious. And every time we teach this, we show examples. We pick weird G0s and show how you get the physical field. You understand? So if that seems hard to believe, or you've got the right feeling. Some things are hard to believe, but true. That's hard to grasp, yes, but true. You understand what I'm saying? It doesn't jump out at you. It's reasonable. So, but it is an essential point to understand the depth of what George Green, 1826, produced. By the way, he couldn't publish. No one would publish the paper. He paid for his own publication. He said, that's crazy. All this kind of talk. You know that, right? He took money and he went to a printer and said, publish it. Because the journal said, the review is failure. Too crazy for us. Okay, so this says valid for any choice G0 that satisfies. Different choices of G0 will derive different applications. So, for the wave field separation methods, the choice of convenience for this expression, not for wave field prediction. Well, first of all, let's see what it says for wave field prediction. This says, for wave field prediction, it says, rho, you need to know that in the volume. You need to have values of the field on the boundary. And if you want to predict a wave in the medium, you need to know rho. What is rho? Rho has that alpha in it. Alpha tells you the difference between reference and actual velocity. So it's saying you need the velocity in this case. Yes? If you made, you understand? If you said, no, I'm going to make my reference velocity the actual in the volume, no problem there, then alpha would be 0, but then those Green's functions would be the ones that in the reference medium would now not be C0 anymore. Okay? So that's already making the statement that to have the field, Green is saying to know the field, predict what a receiver will say, whatever the G0 is, you got to know what's in the volume, the medium properties. Okay, but for the wave field separation methods, we're going to choose here for that purpose, G0 to be causal. If you choose G0 to be causal here, you get the field in the volume, because we said it doesn't matter what G0 you pick. Why we do that is, if you choose G0 to be the causal Green's function, then you can compare this equation to that first equation. This guy. This guy is, if you're integrating over all space, then this must be causal if you want this to be causal. There's no surface integral. You're adding up causal elementary solutions. That'll give you, you add up elementary anti-causal, you will not get the causal. Okay? You can't put G0 minus in there. You understand? So this expression here gives you the field anywhere. It integrates everywhere, all the sources, and anywhere in space. Among all the points in the universe are the points inside that volume that Green's theorem is talking about. So for any R, that expression could be written, instead of infinity, integrate over a volume plus the whole universe outside the volume. And that gives you then that the integral for points inside the volume, those two expressions must be equal. In other words, P equals integral G0 plus rho is true everywhere. P equals integral rho G0 plus on the volume plus the surface integral is only valid for points R in the volume. But in the volume, they must agree, because the field has nothing to do with your math. The field is physical. The field inside the volume must agree no matter how you calculate it. Therefore, you have two expressions for the field in the volume, and when you set them equal, you get that the surface integral here gives you the contribution to the field inside the volume due to sources outside. So that is not a new theory. It's called by different things, by different people. Feshbach, they call it Green's theorem. Born and Wolf, page 100, they call it the extinction theorem. The same theorem. What it's saying is, this guy here is the total field on the surface. It says, if you do that surface integral and evaluate it inside, the surface integral is of the total field. The total field cares about all the sources. It's the physical field on that boundary that you're calculating. If you evaluate that surface integral at a point inside the volume, it gives you the part of the field due to the sources that are outside. That's the extinction. In other words, it extinguishes the contribution due to the sources that are inside. That's what a Wolf called. Or it gives you, half full, half empty. It gives you the contribution due to the sources outside. Okay? Or you can say it extinguishes the contribution due to sources inside the volume to the field inside. So this is a useful tool for different wave field separation methods. So we're going to choose two different reference medium. We're in the marine case. Choose a reference medium here where you have air, or more accurate in the way this is applied, vacuum and water. In other words, the reference medium is air, which is approximated as a vacuum, and water. Then the sources have to be, what do you have to add to this picture to make reality? Yes? Those are the terms on the right-hand side. So what you have to add, to air and water, you have to add air guns, energy source, and you have to add something that turns water down here into earth, a source, right? perturbation. Yes? So you have, in this case, you have a reference medium which is discontinuous and two sources. Then this cable in the water, if you close, let's say a surface this way, like this, that's a closed surface, and do that G grade G, G grade P with this G0. The G0 here has two pieces, like that, because that's the reference medium, yes? It's a two, so with this G0, so if you do that closed surface like that, with the total wave field, and evaluate it at a point below the cable, meaning this inside this volume, it gives you the contribution to the total field at any point in the water or in the earth. That's the portion due to the air gun. Okay. And it cancels the portion due to the earth. So you get what we call a reference field. The field that the air gun or array, without knowing what the array is, you don't need to know. It says whatever the source is outside this volume, which is over here, this is outside, this is the volume, that the wave that that source produces in that reference medium is given by this surface that we're doing. And because these are causal, the Sommerfeld will remove that large radius and you end up with an integral on your cable, okay, of the field and the derivative. This was the basis of a paper in 1990 with Segrest, Tim Keogh, who worked on this at Auckland years ago. And so in the special case that you assume that the source is an isotropic single point, you get a wavelength here, which is this surface integral divided by G0. The deghosting, so that, what does that do? There's an opportunity here, and you're going to see work for how this is going to happen on land. On land, separating the reference wave with ground roll is non-trivial. So this, you'll see when we go through in a minute the agenda, you'll see how ideas like this, set up originally for marine, are going to be looked at for more challenging circumstances. But even in the marine case, this has not been really fully exploited, because when you are in not terribly deep water, so that your reference wave and your reflection data interfere, what often happens is they just cut, and they cut some of that long offset data. This method, now that you have all this acquisition with dual sensors, you can get the reference wave here or in your data, or the reflection data above or on in your data, and predict the reflection data without cutting. Just predict scattered wave. That is something we will pursue this year. That we've focused on this P0 below, but what about getting P0 in your data and removing it? So you get your reflection data at all the offsets you paid for with the long cable. Okay, for deghosting, it's a different issue. And this is the work pioneered by Jin-Feng Zhang, who's at BP now. Ghosts, let's just say, on the receiver side, a deghosted receiver is a receiver that has removed the down wave and has only the up wave at the receiver. Okay, so how does Green's theorem give you that? We're going to pick a different reference medium. A minute ago, to get the reference wave and the reflection data, we picked a reference medium which was two half spaces, air and water, and then we had two sources, air guns and earth. Now we're going to pick a simpler reference medium, a reference medium which is an entire universe of water. And with this entire universe of water, we have to get another source. In other words, to make an entire universe of water into the real world, you have to turn water above the air-water boundary from water into air. Yes? That's the source. Another is the air gun. The other is the earth. Three sources, three additions, in other words, to a whole space of water. Source 1, source 2, source 3. The Green's function here, the causal one, is simpler than before. Before it was this plus this. Now it's just this. Straight propagation. Because it's whole space, yes? Whole space causal. So each of these sources, with that Green's function, just sends a wave away from the source. From the air guns away. From the air away. From the earth away. Just roll away. Okay? So if you pick a point, imagine a point, go back here. Imagine a point, R, where this R is below the source, okay, and above your cable. The point, there's a cable inside the water, and R is above the cable or below the source. At that point, the wave that is coming from the earth is moving up. Because it's rho of the earth, G0 plus, just going up. From the air guns, that wave is moving down, because we picked that position lower than the source. Yes? And from the air, rho of the air times G0 plus is down. So there's only one of those sources that's producing the up component of the wave there. And the up component of the wave is what we want for receiver deghosting. Yes? So the contribution of the source due to the earth, if you could isolate that at this point, you will have receiver deghosted data. That's the whole deal. In other words, at that point I just described, the air, the wave due to the air is down. The air guns, since the point is below the air guns that you've chosen, is down. The contribution due to the earth is up. So if you can find the contribution that the earth is producing at that point above the cable and below the source, you will have receiver deghosted data there, an upgoing wave only. So how are you going to get that? You do a closed surface that keeps the earth outside. Yes, close, go on your cable, close on top. Yes, the source outside now is the earth. That surface integral is going to give you the contribution due to the earth with that reference medium, which is homogeneous. At that point, it's going to be the up wave. Okay. So that's that integral on the right with G0 is just a causal Green's function. Whole space causal Green's function will produce receiver deghosted data above your cable and below the source, for the reason I just mentioned. Let's say you don't have the normal derivative and you want to do deghosting. Then the usual thing people try is, let's put a Green's function here that's not just causal, but vanishes on the cable so that we don't need the normal derivative. When you do that, you can get an expression like this, where this is a point above the cable. This is only if you have a general source that's not a point source, and you want to do receiver deghosting, then you need the field and the derivative. This story here is only for a single isolated isotropic source. But if you are willing to talk that way, that you have a single wavelet from an isotropic source, then this will give you a prediction of the field above the cable, 1 point above the cable. You take its derivative, you produce above the cable a new cable with a field and the derivative on it. And then you proceed to the previous formula, only needing the wavelet and the field on the actual cable. Yes, that's the idea. This has been tested and has shown value. This work is, as I said, in the thesis in great detail of Jingfang Zhang, and then Jim Mayer has worked, and you'll see results on the complicated synthetic and field data, and the impact it has on subsequent multiple removal methods. One point, it's always good to try to get away from all these integrals and try to figure out what's going on with deghosting. Deghosting is basically up-down separation. And if you have some kind of equation like this, where there's a wave moving down, a wave moving up, all you want to know is what's A and B, in particular what's B, up. If you have a two-way wave and you want to make it into a one-way wave, you want to just find one of those coefficients. Well, there's two ways of doing that. One is, if you have the field and the derivative at one depth, you can find A and B to get this expression. If you have the field at 2 points, this is 2 pieces of information at one depth. If you have 2 pieces of information at different depths, you can still find A and B. This is have the field at A at 0 and at A. The field at 2 depths rather than 2 pieces of information at one depth. When you get A and B, the formulas are very different. You have these sine Ka looking things in the denominator, which you don't have if you have 2 measurements at one depth, and where the denominator can vanish with what are called notches, it can be very sensitive to the depth. This will not have that sensitivity. There's no sensitive denominator. So if you're away from notches, then using the field on the cable and saying it's 0 here, or making your Green's function vanish at the cable and at the free surface, anything which depends on knowing the depth of the receiver, either through directly on the field or on its Green's function, will have no issue. That will have no issue away from notches. If notches matter, now in typical cold streamer, it doesn't matter. But as that cable gets deeper, the notch moves in. If you're at the ocean bottom, that notch could be at 5 hertz. So it depends on your frequency, it depends on the depth of the cable. And the same on the source side. Whether you need over on the sources, dual sources. So this is giving the whole general source and receiver deghosting activity. So referencing Jingfang Zhang's thesis. So I think what we'll do is we'll take a 15-minute break now.